this dark energy in the form of cosmological constant, Einstein's original version, is something like 70% of the universe. So you can see that they're not balanced. We also have a sense now of the timeline of the universe. The least certain part of this is the very beginning, but we have a theory called inflation that says the universe began with quantum fluctuations that expanded to astronomical scales, and then we have, for 13.77 billion years, this expansion in the universe, which recently has had this accelerated. 2003, the interesting thing was that all other measurements of cosmology agreed with it. So we had what was called by Science Magazine cosmic convergence. This was the breakthrough of the year cover of 2003, that all measurements were explained by these supreme parameters. However, in 2013, which is when we had our final WMAP results, this was still true. However, just in the short period between 2013 and now, there's starting to be significant tensions developing. So we no longer have cosmic convergence just from these recent measurements. And just to give you one example, I mentioned that we can observe the very early universe and use prediction through the model of what the current expansion rate of the universe is, but we can also directly measure the current expansion rate of the universe. So in 2003 to 2013, those matched sufficiently, but now they're 4.1 sigma in tension with one another if you use the latest high-resolution part of the European flight mission data. And 4.1 sigma is really, I think, too high to be just a statistical fluke. But this is just an example. There are many other tensions, too. And looking more broadly, I no longer believe that this is possible just to be an unusual result. There's something going on here, and there are basically two choices. Either the experiments are underestimating their uncertainties, and it has to be more than one of them, or there's new physics creeping in that we have not taken into account. So if I look forward to the next 10 years, to me, it's essential that we recover cosmic convergence. We need a theory that matches all the data. And how to go about doing that is, of course, to continue improving measurements. Also to be careful to reassess uncertainties in these measurements. It's very important to get those right. And then also to consider new physics, because we don't know which of these possibilities is going on. As I mentioned, this is general relativity is the underlying theory here. And is that right, or is there a wrong GR? Or maybe this dark energy cosmological constant is not the right thing. The cosmological constant, as it's named, is a constant. And maybe the dark energy isn't a constant. Maybe it's changing around in some way that's making this happen. Maybe the dark matter isn't just sitting there. Maybe it's annihilating or decaying. I'm not even claiming that these particular things can even solve the problems of the tensions, but these are the kinds of things that we want to look at. So beyond solving these tensions, looking ahead in the next 10 years is what I call extensions of the standard model of cosmology, things that we sort of expect might be there, but we just haven't been sensitive enough to detect. And so one of the key ones in that category are primordial gravitational waves. This idea of inflation at the beginning of the universe generically generates gravitational waves. And so if we can detect those, that would be a major advance in understanding the beginning of the universe. We're not going to detect those with a LIGO detector like we saw in the last year, but we can detect it from its effect on the polarization of the cosmic microwave background. And so that's a big area. So I mentioned the measuring the tension in the current expansion rate of the universe. If you leave aside the cosmic microwave data and just measure it directly, we have what we call a cosmic distance ladder, where we piece together what's going on. So it's the closest to home with parallax distances, using parallax to determine how far things are. There's a European mission called Gaia, which has already collected a tremendous amount of data that is going to be a big help with parallax distances. And that data is going to be out, I don't know when, but soon, in the scale of 10 years. And that's going to be something to look out for. There's also the James Webb Space Telescope, a sort of successor to the Hubble Space Telescope, launching a little over a year. It's going to be operated off the campus of Johns Hopkins University. And one of the things that we're looking for there is the second rung of the distance ladder, which is the ascending variable stars. They have a relationship between their luminosity and period that we can use to get distances. However, that has to be calibrated, and you want to see them out as far as you can, so the JWST will be helping with that. And then finally, the last rung of the distance ladder are the Type 1a supernovae explosions that you can see out quite far away. And again, the James Webb Space Telescope will help detect those and characterize them better. Right now, the uncertainty in these distance ladder measurements of the expansion rate is 2.4%, which is quite good compared to what it used to be. But the goal here is to get to 1%, and that I think will happen in the next 10 years. There's also a number of plans to do large-scale galaxy surveys. Galaxies are another way to trace what's happening with time through the development of the universe. One method that is very useful is called baryonic acoustic oscillations. All you really need to know about that is it establishes a standard ruler in the universe, which you can move out to different distances and measure angles, and then see the evolution from that. There are many experiments that have been doing this and that will be doing this. The European Euclid space mission is going to launch during the next 10 years, the earlier part of it. I'm on the Euclid team, and it's going to be doing a much better job of than what we have now on baryonic acoustic oscillations. And then one of the other ones, the Subaru prime focus spectrograph, is another one of these that I'm on the team, but there's several other experiments as well in this category. Also, another technique is looking at the distortions of galaxies in what we call weak gravitational lensing. The light comes to us, but it gets bent around gravitationally lens, Einstein says, things along the path. And so we can study that as well, and that gives us the three-dimensional distribution of matter in the universe. So that'll be quite important too. That's actually the main goal of the Euclid satellite. There are other ground-based experiments going on now, and that are continuing. This method we've known about for a long time, but only recently is it matured enough to actually get the interesting measurements out of it. And once again, this is another area where the measurements have tensions between different things. So in terms of the cosmic microwave background in the next 10 years, the concentration of almost everybody in the community is on the polarization of the microwave background. There are a couple of things that generate polarization of the microwave background that I want to focus on. One, of course, I've already mentioned, which is the gravitational waves of the very early universe that polarize the microwave background, and in particular there, and it has these two goals I just mentioned to nail down this sixth parameter that's not that well determined. I think we will do that certainly. And then again, to characterize what happened in the very early universe with gravitational waves, is the inflation theory right? And if so, which inflationary theory? There's all kinds of versions of it. So those are goals. CLASS is the only ground-based telescope that's surveying the cosmic background polarization at its largest angular scales. It's operating now, and we have more telescopes than we're having. So that's my personal view of what's coming in the next 10 years. I wanted to emphasize with these tensions, the standard model of cosmology actually works very, very well. These tensions are very small, but we do have to determine, is this a data problem, or is there a theory? And then we have to extend beyond that to these other signals that might be lurking out there. Finally, just comment that it's not guaranteed that we can learn all of these things about the universe. I included a picture there of the Earth and the Moon from not very far away, actually, and you can really appreciate our planet is just a speck here. And again, there's no guarantee from the speck that we can learn everything there is to know about the universe in its beginning, but we have come a very long way. How much more can be done? I don't know. Thank you. Wonderful. So we have a few minutes for questions. Question from Jill.
You always said plus or minus 10%. How confident are we that that the systemics will not prevent this 1% accuracy that you're talking about?
Yes, that's an excellent question. It goes right to this question of how well we understand uncertainties. What you say is absolutely true, that in the early days of measuring the Hubble constant, there were the camp that said it's 50 plus or minus 5, and the camp that said it was 100 plus or minus 5. But if you actually look over time, that's all been converging. And in the last few years, the key project of the Hubble Space Telescope reported just over 70 with a much smaller error bar, and that number actually has changed very little since then, but the error bar has been coming down and down and down. In terms of whether it's believable, one of the things that I find most convincing about the current measurements is that they're able to take these rungs of the distance ladder and pull one out and put something else in its place, and actually the number doesn't change very much. And that's one of the roles the Gaia data is going to play too in substituting between things there. I'm not in a position to guarantee that it's right, but I can guarantee that the scientists that work on it, and Adam Rees is the main one, and he's next door to me, because I really quiz him on this a lot. They really work very hard to try to get it right. It doesn't mean that the mistake is impossible, but they do all kinds of simulations of systematics and put limits on things. They've approached it very systematically. I take it seriously, and I take these tensions seriously. Another question right here. You can stand up.
Thank you for that wonderful talk. What do you expect from gravitational wave detection in the future with respect to all these models?
Yeah, that's another excellent question. So I thought about putting that on here, but I'm a little uncertain. What we've seen already is that the gravitational waves, just the small number of examples we have, especially one with an electromagnetic counterpart, have already given us interesting information. But the fact that the electromagnetic wave and the gravitational wave get to us with such a little time delay rules out all kinds of other theories. They weren't the standard theories, but they are now ruled out. And actually, that also gave us a measurement of the expansion rate of the universe, the Hubble constant. It is consistent with the other measurement, but its uncertainty is too big to really be competitive. I've been asking Ray Weiss and others, over time, should I be optimistic that with enough of these things that will really help with the Hubble constant? And it's a long story, but the answer is basically there's not that much optimism that the error bar will come way down. It will come down somewhat, but who knows? My gut feeling is that we're going to learn something from the gravitational waves that I'm not thinking about, and that none of us are thinking about, but I don't know that. Anyone? Perhaps I could just ask about the upgrade paths for CLASS. I'm really curious of what's that experiment going to look like in a few years. So CLASS, as I mentioned, is right now we started with one telescope that's been there for a year. I should say, my approach to hardware is very iterative. I don't like designing big things and then learning everything about it at once. I like to learn as I go. Even with WMAP, we did prototyping along the way. So our first telescope is operating. It's doing well, and the second one is shipping out this month, and another one right after that, another one about a year later. And as we're learning about what we're seeing and how they operate, I'm pretty confident that we would like more telescopes and probably ideas for doing better. But right now we have our hands full of what we're doing right now.
Okay, wonderful. All right, let's thank Chuck again for a great time. So, yes, the title is What Can We Learn About Dark Energy in the Next 10 Years? I was asked to focus on the future and the next potential breakthroughs. Chuck mentioned a number of tensions that are starting to creep into the standard model of cosmology, the so-called lambda-CDM model. I'm just going to talk about lambda and lambda-CDM a little bit. And the real question is lambda the right answer for what that first term in the current standard model is? So this graph is probably famous, probably well known to many of you. This is a schematic timeline of the evolution of the universe from the Big Bang, or actually the inflationary epoch in the very far left here. Time is running to the right, and the relative size of the universe is the vertical scale. So we have this this initial exponential growth in the scale of the universe called cosmic inflation that we're trying to pin down and get better evidence to see if that event actually happened. I'm not going to talk about that today. The microwave background radiation on the kind of blue-green screen on the far left is the background radiation the WMAP measured, and that was the baby picture of the universe, the farthest away we can see in the universe with photons, with light. That told us a tremendous amount about the composition, the age, and the shape of the universe. And then the universe has evolved. It's grown by a factor of 1,000 since the background radiation was emitted. And the expansion, for many years, we thought the expansion was slowing down as the gravitational mass of stuff in the universe caused the initial expansion to slow down. But with the supernova results in late 1990s, it became clear that the universe was actually starting to speed up again. The expansion was accelerating, and that idea was really cemented with the WMAP results. Over the last half of the age of the universe, roughly, the expansion has been accelerating. And we attribute that to what we call dark energy, and the best model for dark energy right now is this cosmological constant lambda. But we really have no clue as to how lambda fits into fundamental physics now. It's quite at odds with our ideas of quantum field theory and what we know about standard model of particle physics. So that really is one of the great challenges going forward. To try and get a better measurement of dark energy, and that's that leads me to the subtitle of my talk. This will be Giving the Universe of Time. Time is another acronym like MAP, but I'll tell you what it means in a moment. But it's a novel new telescope for cosmology that I will talk about more shortly. This is a nighttime shot. I guess you can't really see the night sky very clearly in this view, but this is a very good looking telescope, and I'm going to tell you why we built Chime and why it looks so funny. The most important, I think, to take away from the microwave enormous field of view, an instantaneous view of the sky at any single time. And this kind of design helps us do that. We cover half the sky. We're going to try to map half the sky visible from Canada, and we do that every day. But this enormous field of view, I'll describe a little bit about that. The frequency range of that is in the radio frequency range. It's 400 to 800 megahertz, which, I should say that the point of the measurement is to map neutral hydrogen gas. We're using the 21 centimeter emission line, which is the most abundant radio emission line that neutral hydrogen puts out. And then we're looking at that in a redshifted spectrum frequency range. So 400 to 800 megahertz corresponds to looking at a cosmological history of the universe as roughly a third to a half of its present day age, or a redshift of roughly 1 to 2 in vernacular. And so China's a working telescope that operates over this entire optic wavelength, 400 to 800 megahertz, to measure this redshifted 21 centimeter line, to map the distribution of neutral hydrogen on large scales, which is the distribution of galaxies on large scales. So just a couple of slides about how Chime works conceptually. We have these cylindrical telescopes. We place a single receiver at the focus of the parabola, the cross-section of the cylinder. The radiation from that will be focused onto the sky, and that receiver will be sensitive to an enormous swath of the sky overhead, roughly about 2 degrees across in each direction, and 120 degrees in the north-south direction. And so that's what gives Chime its enormous instantaneous field of view. But the single receiver has almost no spatial resolution. You can't tell where that blue swath of the radiation came from, so it's a useless receiver for mapping the sky. To actually get spatial information or localization information, you need to have a whole bunch of receivers. If you take a pair of them, then this pair of receivers is sensitive to a sequence of hot and cold spots along the north-south direction. And you can use that combination of information to start to localize where the radiation is coming from. If you fill the entire focal line with receivers, with a microsampling, if you like, then you can start to then reconstruct the north-south position information, realize where radiation is coming from, by combining the information from all these receivers simultaneously to see where the north-south direction came from. And finally, if you have 4 cylinders and you put them all together, you can also do the same kind of thing by combining the cylinder with information in the east-west direction. And you can simultaneously basically reconstruct beams, if you will, on the sky that completely fill this field of view. And so you can think, and then the sky rotates overhead once a day, and so this entire sweep of beams expands across the sky every day and measures and maps the sky. So that's what gives it the enormous mapping speed that is required to get a large volume survey of the universe. And so this, the red slash there indicates kind of what the view of a single receiver. This is in a coordinate system where the celestial equator of the Earth is across the middle of the band. Celestial poles at the top, and you can see how the galaxy arcs across the sky in this rendition.